For 62 through 65, we're just trying to identify the transformation. On 62, outside of the functional machine, outside of the absolute value, we're subtracting 5. That simply means we're moving down 5. Notice on 63, this is inside of the squaring function. That tells me it's going to be horizontal movement. Now I have to be careful here. X minus 4 actually means go to the right 4. And what may help is ask yourself what would make it 0. Using the zero factor property, positive 4 would make it 0. When I multiply a function by a number, that's going to vertically stretch or compress it. Since 1/2 is smaller than 1, this is going to be a vertical compress or shrink. You can call it compression or shrink by 1/2. And number 65, when we multiply a function by a negative, that flips it. This is going to reflect over the x axis. It's a vertical reflection, which is a reflection over the x axis. For number 66, now we're actually graphing these. I like to always list what's happening. The +1 inside there with the x is going to move this to the left 1. Multiplying the function by 2 is going to vertically stretch by 2. So normal cubic looks something like this. It's hitting at the origin, it's hitting at 1, 1, it's hitting at -1, -1. This is going to be pushed to the left 1 and pulled vertically by 2. So my center point, or the middle of this, is going to be moved to the left 1. And now from that middle point, the other 2 points that I had up there originally were moved over 1 and vertically 1. Since it's being vertically stretched, they're going to get moved over 1 and then vertically 2. Over 1 and then vertically 2. That's going to account for the vertical stretch of 2. So from that first point, that's where the other 2 points are going to be. Remember, what you can always do on these is make a little XY graph, or sorry, table. Since I knew this moved left 1, -1 was my first point, I'd like to pick a point on either side of that, like -2 and 0 for x. If I plug -2 into the function, it outputs a -2. If I plug 0 into the function, it outputs a 2. Those are other points on this graph. And so I get a more stretched out cubic function. For letter B, my function is -√x + 2 + 5. Again, I like to list what's happening, starting with what's happening to the x. +2 is going to mean go left 2. The negative outside is going to cause an x reflection. The +5 is going to move this up 5. So the normal square root function looks something like this, the parent. I know that my starting point is going to move left 2 and up 5. So I know that my starting point going to be left 2 and up 5. And I know instead of going up, this is going to be going down because of that x reflection. And again, if you're struggling to find other points, make yourself a table. Now I need to be smart in what x's I pick, especially with the square root function. A good pick would be -1. If I plug -1 into this function, that's a 5. That would give me, let's see, negative square root of 1 plus 5. So the square root of 1 is 1. So it's -1 plus 5, 4. So -1, 4 is a point. Another good pick for x might be, let's try +2. The reason that's nice is I know that's going to give me a nice square root. So that would be negative square root of 4 plus 5. So that's going to be -2 plus 5, 3. So at 2, I'm at 3. And there's my square root curve. Number 67, we're asked if this is even, odd, or neither. The test to see if this is even is basically if I replace the x's with negative x's, do I get the same thing back? Well, taking them to even powers, go figure, gives me the same thing back. So negative x to the 4th is the same thing as x to the 4th. Negative x squared is the same thing as x squared. I got the same thing I started with. That tells me that this is an even function, which again would mean that it has a y-axis symmetry. This function would end up looking something like this. On number 68, now we're getting to operations on functions and composition of functions. Part A wants f minus g of 6. What this essentially means is find f of 6, find g of 6, and subtract them. So f of 6 would just be plugging 6 into the f function. That would be 6 minus 4, 2. 2 squared is 4. G of 6, that would give me 3 times 6 minus 1. So that's going to give me 17. So 4 minus 17 gives me negative 13. And we're good. For letter B, fg of -2. This is multiplication, so this means find f of -2. Multiply it by g of -2. So f of -2, if I plug -2 in, that's going to give me -6 squared, which is positive 36. If I plug -2 into the g function, that's going to give me -6 minus 1, which is -7. If I multiply those together, I'll get -252. Part C starts to get into composition of functions. G of f of x. This means, I read these kind of right to left. It means take x, plug it into the f machine. Okay, well that simply is the f machine. But then take that entire machine and plug that whole machine into the g function. So what is that going to look like? Well, the g function is 3 something minus 1. That something that I'm plugging in is the entire f function. X minus 4 squared. And we can go ahead and just leave it like that. For letter D, we're doing h of g of x. Again, I kind of go right to left here. If x went into g, that would just give me the normal g function. But now that entire function is going to get plugged in for x in the h function. So the h function is absolute value something minus 1 plus 3. The something that I'm plugging in is the entire 3x minus 1. And then if I just clean this up a little bit, that would be absolute value 3x minus 2 plus 3. For number 69, we're asked which functions are one-to-one. The easiest way to attack this is to think of what the graphs look like. A one-to-one function passes the vertical line test. That's what makes it a function, or part of it. But it also has to pass the horizontal line test, meaning a horizontal line would only hit the function once. Well, part A is a parabola. A horizontal line would hit that more than once. So this is not one-to-one. Letter B is just a line with a slope of 3, starting down 1. Any horizontal line would only hit that once. It doesn't matter where I drew the horizontal line. So yes, that is a one-to-one function. Letter C, absolute value functions, look like a V. A horizontal line would hit it more than once. That means it does not pass the horizontal line test, and it is not a function. Number 70, we're asked to find the inverse of the function. Inverses basically flip the x's and y's, kind of in the most basic definition of it. Think of my f of x as being like my y. I'm going to flip x and y, so turn this into x equals y minus 5 cubed plus 1. Now I'm just going to isolate that new y variable. So the first thing I'd have to do is subtract 1. So now I'd have x minus 1 equals y minus 5 cubed. The next step would be to take the cube root of both sides. Remember, cube roots, I do not get a plus or a minus. So this would give me the cube root of x minus 1 equals y minus 5. And the final step would be to add 5. Now realize this adding 5, it does not go inside of the cube root. It was after I took the cube root. And that's what my new y is. And we can call it the inverse, so we can use that inverse notation, f inverse of x. There's the inverse function. On number 71, we're given a function. It definitely looks piecewise, but we just want to graph the inverse. Again, remember, in its most basic terms, an inverse just flips the x's and y's. So this point over here at -4, -1, I'm just going to flip the x's and y's, and I'm going to plot -1, -4. The next point on the original function was at -1, 3. Flip the x and y. 3, -1 must be on the inverse. And the final point is sitting at 5, 4. Flip the x and y. 4, 5, about right here, would be on the inverse. Connect the dots. And there's my inverse. Also of note, remember on the inverse, it perfectly folds over the line y equals x. And I can see that the original function and my purple function are perfect folds of one another.